Okay, so let me go back with a little bit of history. Actually, our capability of retrieving aerosols in the UV was the result of a fortunate discovery in the mid-90s, when we transitioning from one version of the ozone retrieval algorithm to other, we discovered that actually we have sensitivity to aerosol absorption in our data. So that sensitivity today is well known as the UV aerosol index, which is basically, as it's defined there, the difference in spectral contrast between the actual measure radiances and the calculated radiances for a pure Rayleigh atmosphere. So the difference between these two calculations is known as the aerosol index. And initially it was reported just as the simple difference in reflectivity at two channels. And I will actually be referring to that difference instead of the UV aerosol index as defined before, just for convenience. They are basically a proxy of each other. So as I said, this index actually is very well correlated with the presence of aerosol. It depends on the aerosol optical depth, single scattering albedo, and aerosol layer height, which is very, very important. This is the reason I am going to be talking about that here. There are other sources of aerosol in the signal, but they are not as important as the signal from the aerosol itself. There is ocean color generated signal, and there is sulfur reflected generated signal, but they are all second order compared to the aerosol absorption signal. So we have been applying this technique to a series of instruments, for instance, since TOMS. You see all the instruments listed there. And actually, we have been able to develop a routine to actually convert the qualitative information of the aerosol index into the right parameters of optical depth and single scattering albedo. That scheme that shows there, it shows the sensitivity of the ratio of the two channels against the longer channel in terms of the single scattering albedo and optical depth. So if you know the aerosol layer height, you can actually do a direct retrieval like that and derive the values. But of course, without knowing the aerosol layer height, we need to assume something, and that's subject to uncertainties. However, we have always been working with the making some assumption of the aerosol layer height. In the beginning, during the TOMS period, we basically use calculations from a model and assume the aerosol layer height. Later on, for OMI, we were able to generate a climatology of 30-month global climatology of aerosol layer height from Calypso and OMI collocated measurements, and came out with this kind of climatological representation, and actually up to date, we are using that. The climatology was that short because, unfortunately, we lost, you may be familiar with the raw anomaly effect, a feature of the OMI data. We lost a section of our viewing angles, and as a result, the collocation that we had with the Calliope was lost, and therefore we ended up with a very short term, 30 months to produce that climatology. And now with the current new sensors that have combined UV capability as well as oxygen B-band capability, we have been able to transition into having to use a climatology and actually doing retrievals of the aerosol layer height using the oxygen B-band observations. And this is an example of that. So on the panel on the right shows the aerosol presence, dust mainly, and a little bit of smoke in terms of the aerosol index. And then from the same event on July 2nd, 2018, we had retrieved aerosol layer height from the oxygen B-band, and you see how we actually do a reasonable good job over the oceans, we retrieve the features and over the dark surfaces as well. However, you see that over the Saharan desert, the retrieval capability is quite limited. We get a few spots here and there, but we are not really doing a full retrieval of the aerosol layer height with the oxygen B-band. That's because at that wavelength, the surface reflectance is very high, and the technique has strong limitations to work well. That's what brings us to the limb profiler as an alternative. Okay, let me see. I'm here. Okay. Well, we have already seen this a picture that shows actually the two sensors on the same satellite, and the OMPS and the LP are automatically collocated, as we can see in the figure on the right. You see that each of the slits is actually very well collocated, associated with specific positions of the mapper. So the collocation in terms of the two measurements is quite straightforward when you use the native mapper information together with the limb profiler. Doing the collocation with other sensors is going to be more complicated, but also doable. So, okay, this is an actual case I'm going to be looking in detail. This is actually an event on June 7, 2020. You see on the right an RGB image from MODIS that clearly shows the presence of a very thick aerosol layer. Actually, this plume, these events in 2020 were labeled as a Godzilla dust plume. It's very optically thick. You can see the same plume in terms of the OMPS aerosol index on the right. And actually, you see indicated that the overpassing or the three slits of the map of the limb profiler. Now, we also in this analysis we also calculated the new quantity using the direct measurements of the limb profiler at 430 and 350 nanometer. Using normalized radiances at 47 kilometers, we calculated an equivalent limb reflectivity that can be used, the difference between the two reflectivity from the two sensors, so the R380 and 340, the standard aerosol index, let's say, from the mapper, and the 430, 350 would be the equivalent quantity from the profiler. If we plot that information as a function of latitude along the orbital track, you see that the magnitude qualitatively is a very good agreement, the one that we get from the mapper on the right, with the one obtained for the three slits on the left. So basically, this is telling us we are actually picking up the same signal of the aerosol index with the limb profiler itself, and then we can, in the absence of absorbing aerosols, this line will practically be zero or slightly oscillate around zero. But with this large magnitude, it clearly shows the presence of absorbing aerosol. So clearly, that's the first step. We are detecting the absorbing aerosol, and then now we can move to the next step, which is actually feeding up those profiles. So we get for the three profiles, where I refer to them as west, center, and east slits. We can feed each of those profiles independently to our standard retrieval algorithm. Instead of assuming an aerosol height, we feed the profile directly, procedure with the retrieval, and come out with the results. And you see in the bottom, we have the retrieve fields of the optical depth at 379 nanometer and the single scattering albedo. And those numbers are very, very, very smooth with less oscillation. But when we use the climatology, the data is a lot noisier. Here we see a very smooth field with both parameters, with optical thickness, in this case, between about 1 and 3. This is a very optically thick layer. And the single scattering albedo also in the range of about 0.85, well, not 5, but like 0.87 and 0.93 or so. So this is a very good result that shows that actually we can use this information to produce our retrieval. This is extended to an additional orbit. Before I just showed it for 623, now we have 2 more orbits. In the third orbit, there's not much information, but we still get the information of the second orbit. We get the information on these retrieve parameters. This is just a sort of a comparison with the places where we have the signal. Somehow we want to correlate this with the aerosols as seen by Calliope. There is no exact collocation, but it's in the same region and it's consistent with what we are retrieving. So with that, I finish my presentation. So we can actually very advantageously combine this information to retrieve the aerosol optical data single scattering albedo over the deserts, which is an area where other techniques don't work. We successfully use the retrieve profile. We don't really need detailed information on the high. Having the profile is even better. You just feed the profile directly to our retriever algorithm. This also can be applied with other sensors, but the collocation will be more complicated, but it's still doable. So, as we all know, the main limitation of LP information for characterizing tropospheric aerosols is the presence of clouds. But over the deserts, this seems to be less of a severe problem than over other regions. So we are actually beginning to work with this data, and our idea is to produce an OMPSM mapper algorithm. What I showed you here is a demonstration analysis, basically. But we intend to do this in a quasi-operational product. And that's it.